So today's topic is about Rust and WebAssembly. So in this presentation, I am going to implement a simple web application with WebAssembly using JavaScript and Rust. So I will give you a brief idea about WebAssembly, Rust, and then I'll move on to my demonstration. So first about WebAssembly. So the WebAssembly is first appeared on 2017. So Google, Apple, for Mozilla and W3C, like huge tech companies, originated and sponsored to this concept. As you know, JavaScript is slow when compared to C and C++, like strongly typed languages. So when running a computational heavy task, JavaScript doesn't perform well. So with the help of this WebAssembly, you will be able to run C or C++ or Rust-like languages inside your browser with the near native speed. So we don't have to depend on JavaScript every time. So according to the webassembly.org website, WebAssembly is defined as a binary instruction format for a stack-based virtual machine, and also it is abbreviated as WASM. WASM is designed as a portable compilation target for programming languages, enabling deployment on the web for client and server applications. So in simpler words, WebAssembly is a code that has been compiled for the browser. So which means instead of using JavaScript for everything, every front-end operation, we can use other WebAssembly supportive languages for performance-sensitive areas in your web apps. So this WebAssembly code runs in a virtual machine called a stack-based virtual machine. So which is very small, portable state machine, and it is integrated in your web browser. So at the moment, all the modern web browsers have this support. Okay, as a simple as an overview, so let's consider about this simple front-end application. So we have this index.html file where we render in the browser, and we have the entry point for the JavaScript. We call it as app.js, and we have styling of the application, and then we have this WebAssembly file which runs on the browser's stack-based virtual machine. So according to this example, you can see in this WebAssembly file has implemented this add and subtract methods. So in the JavaScript side, we call these methods with the relevant parameters, and then this WebAssembly run on this virtual machine, and then it return the value after the calculations, and then only we can interact with the DOM and do whatever the changes you need to do in the UIs. So basically, this WebAssembly file does not communicate with the browser's DOM. It only interact with the JavaScript file. That's the very high level idea of WebAssembly. Let's move to the Rust. Rust firstly created on 2006 by one of the employee from the Mozilla, and then later the Mozilla sponsored to this and continued the development. So this is very similar to C and C++. So it has this very similar syntax, and also Rust can also be used with the similar purposes that we normally use in C and C++. So with the time, so this has become very popular now, and according to the Stack Overflow's the stats, I found this stat. So in there, Rust is considered as the most loved programming language in this 2021, and also in the previous year as well. So as you can see here, you can see the rates, the percentages. The Rust has 86.1, which is very high compared to the other languages. And in terms of features, Rust gives low-level control to the developers, like in C and C++, and it also gives reliable performance. So the currently it has used in different areas like scientific experiments, like that. And also the most important thing is this it is designed to be a memory safe. Uh, as you know, C and C++ is not memory safe. There are a lot of errors you may come across because of this. But unlike C and C++, Rust is memory safe. But also it does not have a garbage collector. Uh, so how does it keep the memory safe is the Rust has this memory management system that is based on this concept of lifetime that lets the compiler track at compile time when memory is allocated and when it is freed. So it's called ownership and borrowing concept. And so anyway, so this is the basic idea. So I'm not going to go deeper in this topic since it is not in our scope. So I choose this Rust for this WebAssembly application because of it's becoming one of the go-to language just for the WebAssembly related applications. And it has a fair amount of developer community and also a good existing libraries, so we can reuse them in our projects. And the other thing is it plays very well with the other front-end technologies like TypeScript and ECMAScript. And also it has a different package manager called Cargo, so which allow to manage our libraries easily like npm. The Rust. So let's move on to the demonstration. So before moving to the demonstration, so first we have to install the Rust compiler. You can download it from this URL. So which includes the Rust C, which is the compiler, and also the package manager called Cargo. Other than that, you have to download this WASM pack library. So which is this allows to compile the Rust programs to WebAssembly, and also other than that it gives you a JavaScript wrapper around the WebAssembly file, so which is very cool. You can just import that JavaScript function and you can just directly use it in our web app. And other than that, it provides some features like we can straight away add our Rust generated files as a npm library, so we can publish into a npm repo, and the other people who wants they can use it. So there is this it gives that kind of features. Other than that, I know it also generates the package.json file, which we need to have in a normal node module. And other than that, we need to install this cargo generate. So I'm going to use this one. This is more like a create react app library. So it gives some existing templates to use. So we can when we are starting a project, it will we can use one of the templates to start off the project. And you know what npm is. Yeah. So let's do some coding first. So as I mentioned, so this is the place where we can download the exe file for the Rust compiler. So you can download any of the exe files. So if you are a Linux user, you can download it from this command. And this is the link for WASM Webpack library. It's also there's an exe file, and also provide some URL for the Linux users. So once it is installed, so here I have opened just an empty folder with using Visual Studio Discord. So since I have already installed them, so for example, if you have properly installed it, you can see the version by checking the version. So it will give you a version for the cargo. And as I mentioned earlier, now we have to install the cargo uh, generate module. For that, I'm going to use cargo install. Okay, it should now install the cargo module. So I have already installed that one. And then so for the demonstration purpose, I'm going to use this existing template called WASM pack template. So I'm going to this has some basic file structure where we don't need to create them manually. So I'm going to use this one with the cargo generate. So that we can use the cargo generate function. We have to give a project name. I'm going to give you as the project name. It has been created the file structure. I'm going to open. So it now we can see the files. So these are some of the files that has been added by the author, and we can so I will give you some idea about some of the important files here. And this cargo.toml file, this is like a package.json file in normal web application. So it has some metadata about the project and as well as some of the dependencies. For the moment, it only have this WASM bindgen dependency, so which allows to expose our Rust functions to JavaScript. And so later in the demonstration, I will show you how it does. Yeah, that is about this file, and these are some of the files that's been added by the author. And this test also, I think that is also a dependency that has been in there as a dependency, so which we are not going to go through it. So the main file that we should focus is this lib.rust file. So in there, this is like the entry point for the project. In Rust. The interesting thing is in the Rust, there is a new vocabulary in there. So normally we call this as a project, but in the Rust programs we call it as a Rust crate. So this is the like main file in the Rust crate. So inside the crate there are modules. For example, this utils.rs is a inbuilt module. So where we can write some utility functions. For the moment, we don't need that, so we can ignore that. So let's go to this lib.rs file. Here we have import this module called utils, and then this is the dependency that we talked about, the WASM bindgen. So it is also imported to here, and this valloc is it's like a mimifier. For example, so when we compiling this to WebAssembly, so we need to optimize as much as possible to reduce the code size. As you know, normally when we are loading in a web application, sometimes we might need to get this file from the internet. So the file size is very important. So what this is enabled as a global allocator in this main lib.rs file, and it will optimize the compilation process, and it will give the lowest file size for the WebAssembly file. And this is the WASM binding, so we can call this create function inside the JavaScript. So that's why we have to annotate this as a WASM binding, and this is a public function, and we use this JavaScript's native alert to say hello world. So here we have this alert called hello world, and this is where we import it. So we use this external keyword to get some libraries so functionalities from different or foreign environments. Yeah, that's about that file, and we can now build this file. For that we can use some it might take some time to build. So while this building, so this is only this only contains the Rust related files. In order to show it this inside a browser, so we need to have a front end application, right? For that, I'm going to use this existing template called create WASM map template. So it is also a simple front-end application which is hosted using a Webpack dev server. So I'm going to use that one. Anyway. So now I have no. So build is also success. So I'm going to create a new folder and create a front-end application. They are using that template I showed you. So this will create a new a directory called www, and then the library will be created there. So yeah, so now it has been generated. You can see this www folder. Yeah, before that, as you can see, once we build that our WebAssembly code, there is a new directory called pkg, so package directory. So this is simply this can be considered as a simple node module. So basically using that WASM pack library, so it's generated this readme.md file, which is copied from the root project's readme.md, and also it's generated the package .json file here. This should include all the dependencies if we have used any, and also other than some metadata as well. And this WASM file, this is the compiled WebAssembly file. So this is the file that we that the browser runs. Other than that, as I mentioned earlier, this WASM pack library build this wrapper. So we can just import the library, and then if we call the greet function, it will call this WebAssembly's greet function. So it is here it has imported the WebAssembly file, and this is the simple wrapper. But for our purpose, it won't. You might think this is not very important, but when it comes to the complex scenarios, this might be very useful. Other than that, we have this d.ts file which includes the TypeScript declarations if you are using a TypeScript in your web application. Yeah, that's about the package that we generated. Now if we move to the www folder where we create our front end, and here for in there we consider about the file structure. We have this webpack.config.js file. So it has all the configuration related to the Webpack dev server, and we have the package.json file and all the other license and some author added files, and we have the index.js file where this is the entry point for the JavaScript entry point for the web application, and this is the HTML file where we render the data in the browser. Yeah. So what we're going to do is first, so it has some. First, we need to install our package that we generated. For that, I'm going to add it as a dependency here. So I'm going to okay, so I have pointed this to the directory that our built. So this is the name that we have given for our library. So I'm going to copy that one and use it in this JS file. So currently it has this hello WASM that it is also a library that also do the same thing. So we're going to remove that one and use our module here. So before that also we need to do an npm install here. Okay. Now we have to go inside the www folder and npm install. Okay, while it's installing, so if you have any questions, you can ask. Uh, okay, so finally it has installed all the dependencies. So then I can run it by npm run start. Okay, it has been compiled successfully. So we can. So once you go there, so it will show and says hello GUTech. So yeah, that is the thing that we added. That is the text that we added in the WebAssembly file. But if you are not sure, if you have any doubts, so let's do some change into this file. So let's delete this one and say hello world. Save, and then you can build it again in this command. then if you go to the browser and reload, and you should say it shows the hello world. So that means so this is happening from the WebAssembly code. Yeah. That's about the hello world. Okay, before moving to the demonstration, let's move some I'm going to give some explanation about what I'm going to implement. So I'm going to implement this Conway's game of life algorithm, so which is very famous algorithm in data structures and algorithms. So it contains this infinite two-dimensional orthogonal grid, and and in this grid, in this grid, there are cells. So each cell has two status called dead or live. So these white cells are uh, dead cells, and these black cells are dead cells. So sorry, alive cells. So we normally what we do is we are going to retrieve the second generation from the first generation. So in order to do that, there are four roles. So if we talk about the rules, any live cell with fewer than two live neighbors dies, as if by caused by underpopulation. For example, if you talk about this cell, so this is the neighborhood of this cell. So if we can count at least two live cells within the neighborhood, and that cell will alive. But in this case, it has only one live cell, so it will be dead in the next generation. So the other rule is any live cell with two or three live neighbors lives on the next generation. So if we consider about this cell, it has two live cells, so it lives in this generation as well. The rule is any live cell with more than three live neighbors died as if by overpopulation. So if there is a cell which has more than three live cells, so it should be dead in this generation. And the other is any dead cell with exactly three live neighbors becomes a live cell as if by reproduction. For if we consider about this cell, so it has three alive cells, so it will become alive in this generation. The same rule applies here. So this is the rule set, and this is what we are going to implement inside the application. And so the other thing is uh, we are going to implement this flat array to implement the grid. For example, let's say the grid is 4x4 array and 4x4 grid. So this will the grid will be represented by a 16 slot array, where the first four slots will be the zeroth row, and the second four slots will be the first row. Likewise, and if you want to access any given cell, uh, if we were given a row and a column, so we can access it using this simple formula. So where we can multiply the row with the width of the universe, and we can add the column. For example, if you want to retrieve this the first rows, the second column, the third column, so the row is first, and the width of the universe is 4. So this gives 4, and the column is see one. This is the second column, right? So we start from the 0th, so it will give 6 here. So this is the position of that cell, index of that cell. So that is how we retrieve the cells. And also I forgot to tell you that for the neighboring cells, which has some neighboring cells, when we use these edge cells, so the neighboring cells are that wraps around the other side of the universe. For example, if we consider about this edge, this cell, so it has these three neighboring cells. For other cells can be, for the other neighboring cells would be these two, for this one, and also this two for this in, for this empty area. So that is how we going to implement. We are going to implement. Yeah. So let's move into that. So in order to save the time, so I have already for that thing we need to stop. Okay. So this is the same file structure that we used in the hello world. So here in the lib.rust file, I have implemented this the logic for this the game of life. For example, the each cell is represented as a struct called cell, and there are two status, dead and live, and this is also exposed to JavaScript, and each cell is represented using a single byte. This is how we define that, and also this is this struct can be copied, cloned, and print, and also it is comparable. So that is how we define it in uh, this Rust applications. And also, if you want more, you can manually edit this as well. That's about the cell. And for the universe, there is another struct, and we take width and height as 32-bit integers, and also it includes the cells as vector, and we are going to implement this universe trait. So in the Rust, we normally call interfaces as traits. Uh, the trait is simply normally when we are using C++ or Java, we call them as interfaces, but in Rust we call them as traits. So there are a whole lot of new words in there that we normally don't use. So here is the constructor. So we have given the width and the height as 64. So the grid size will be 64 by 64, and we will assign some random data for the cells for the liveness or the date. And these are some of the functions that are exposed to JavaScript that we may need. For example, we can get the width of the grid and height, and also cells as a pointer. And other than that, so this is the logic that I mentioned earlier to retrieve the index of a given cell. So if we give the row and the columns, it will give the index of that cell, and then we need to count the number of live cells in that particular cell's neighborhood. So this is what this function does. So it will loop over, and it will be count the number of live cells. And ticking is what we do when we go compute the next generation. So once we tick, so we will check if there are when we do the checks, and based on that, and based on the for rows, we will give change the status of the cells. Yeah, so this is what this function does. And other than that, there is the display trait called display. So we are going to implement that in order to display this the grid in our browser. So which is basically a text output. Yeah, that's about that WebAssembly file. So I'm going to uh, build this one. Yeah, now it has been published to this package directory, and then if you go to the www folder in the index.js, so and the package.json, we have defined that dependency as WASM game of life, and we have directed to pointed that directory that we generated before. And the index.js file, we can import the file, the library, and we can use it. So this is where we initialize our universe, and then we are going to use this request animation frame, which is a native function to render something infinitely in JavaScript. And the index.html file, we are going to use this pre tag, which allows to render some text output. So for the first time to initialize, we will call this request animation frame the render loop. So this will run infinitely. So each time it will tick, and it retrieves the next generation from the existing generation, and it will render in the browser. That is the expected behavior. So we can it has been compiled. So as you can see, now it's working, and it's generating generating the generations from the previous one. So it's runs infinitely. So in order to like slow down the process, we can use some set timer here. Two seconds. So you can see now it's the process has been slowed down. Um, yeah. So that is the basic.
Lakshan, what was the initial condition for this? Initially, what is were
Here,
the
Hetu,
live
so
cells
we are just
random?
yeah. So we have this here we have just assigning based on this mode operation. We are just assigning random. Random means we are just like getting the mode from 2.7. The condition is true, it's live. Otherwise, it's dead.
All right, got it.
Yeah, so base is the basic idea, but there's one thing that need to remember is, so when we are implementing a WebAssembly, we need to make sure the communication between WebAssembly and the JavaScript side should be minimum. So otherwise, there might be an overhead between that communication, and we have to compromise the performance again. So for that, we need to do all the calculations from the WebAssembly area, and once it is done, we can just retrieve the data and show. So in this example, so what we did was we just rendering it inside the WebAssembly, right? Using this method. So, but instead of that, maybe we can try out. We can just retrieve the next generation data from the uh, WebAssembly, and we can display using JavaScript. So in order to do that, there's a, so I'm going to comment out this one, and there is a JavaScript code where we're going to only retrieving the next generation cells, and we draw it inside the JavaScript. Uh, since we don't need to display it using WebAssembly, because JavaScript is what is the most suitable thing for that. Okay, now this is like a simple JavaScript algorithm to generate that grid that we saw earlier. So I'm going to generate that using this one, and also in the industrial HTML we're going to use the canvas tag instead of tree. Okay, as you can see, now only the generated status come from the WebAssembly function, and the rendering part is done using JavaScript. Yeah. That is actually very much it I wanted to to show you guys. So if you have any questions, you can ask.
Tharindu, did you also found any .NET C Sharp, any popular tools for WASM compilation? I know we have that
Uh,
.NET has that Blazor,
yeah, that
which
is the one I
compiles.
found.
Yeah, but without, I mean, there we don't necessarily directly use the compiler and everything like Rust. But
Yeah.
did you find any other projects which you use the compiler like you used in Rust without Visual Studio?
Uh, no, Ravi, but I think there are some like real world applications. For example, Figma. So there is a web uh, version of Figma. So in there they have used the C++, I think. Um, so that is how they use WebAssembly.
I was actually surprised to hear that Rust is the most favorite language in Stack Overflow.
Yeah, it's the I think it's for like 4 or 5 consecutive years it has been there. And initially it was came to it's like a challenge to C++, but with the with the applications that C++ has, we can't people don't like to go to see Rust by just ignoring the existing projects, uh, and also with the history. So that's why it doesn't become very popular, I think. Anything else, guys? Okay, seems like no. And thank you for listening. And here I have attached some of the references that I used for this presentation. Okay. Thank you.